channel. I hope you are all doing well. In our previous video, we learned about the relations, their definition, and some basic examples. If you have not watched that video yet, I strongly recommend you to watch it first because today's topic is based on that concept. In this video, we are going to learn types of relation. It is a very simple and easy way. We will clearly understand the reflexive relation, symmetric relation, transitive relation, and last one is equivalence relation. Okay, so let's begin our lesson with the first type of relation, that is a reflexive relation. Then what is a reflexive relation? A relation R on a set A is said to be reflexive if every element of set A is related to itself. Be careful. I will go through the example, then it will be clearly you can understand. Let set A contain the three element be a set. Then the ordered pair 1 comma 1, 2 comma 2, 3 comma 3. It means that what is the set A contain that all the element of set A is related to itself 1 comma 1, 2 comma 2, 3 comma 3. It may contain extra element, but all the element of set A related to itself means then that relation is called as a reflexive relation on set A. Therefore, look at here. Thus, R is reflexive. It implies ordered pair A comma A belongs to R for all A belongs to set A. It means that ordered pair A comma A belongs to R. It should be satisfied for all the element of set A. Then only it is a reflexive. Look at the example R1. It contains the ordered pair 1 comma 1, 3 comma 3, 2 comma 1, 3 comma 2. In this, the ordered pair 2 comma 2 is not there. That's what 2 contain in the set A, but it ordered pair 2 comma 2 not in the relation. Therefore, the relation R1 is not reflexive. A relation R is not reflexive if there exists an element A in the set A such that ordered pair A comma A does not belongs to R. That's what R1 is not reflexive relation. Okay, now here how many reflexive relation we can make on the set A which contain the n element? If n of A is n element is there, then number of reflexive relations, be careful, this is very important, number of reflexive relations on set A is 2 power n into n minus 1. This is the number of reflexive relation on set A which contain n number of element. Next, second one, that is an symmetric relation. What is a symmetric relation? A relation R on set A is said to be symmetric. Relation R on a set A is said to be a symmetric relation if ordered pair A comma B belongs to R. It implies B comma A also belongs to R. It should be satisfied for all the element of an A comma B. It should be in the set A. Okay, na? That is an if A related to B, it implies B also related to A for all the element of A comma B belongs to set A. Then only this relation is said to be symmetric. To make you to clarify, I will take one example here. Let set A which contain the four element. I define the two relation R1 and R2 in such a way that R1 1 comma 3, 1 comma 4, 3 comma 1, 2 comma 2, 4 comma 1. R2 I defined in such a way that 1 comma 1, 2 comma 2, 3 comma 3, 1 comma 3. Look at the relation R1. R1 is symmetric relation because look at here, 1 comma 3 is there, they reverse, 3 comma 1 is there, 1 comma 4 is there, 4 comma 1 is there, 2 comma 2 is there, that reverse also 2 comma 2. Therefore R1 is symmetric relation on A because A comma B is in the R1. It implies B comma A also belongs to R1. That's what relation R1 is symmetric. Look at the relation R2. 1 comma 1, okay, reverse also 1 comma 1, 2 comma 2, 3 comma 3, okay. Look at the last ordered pair. 1 comma 3 is there in the R1 but 3 comma 1 is not there. That's what R2 is not symmetric. Okay, then one more important you should remember, a reflexive relation on set A is not necessarily symmetric. Look at the example here. Relation R contain the ordered pair 1 comma 1, 2 comma 2, 3 comma 3, 1 comma 3. This is relation defined on set A which contain the 1 comma 2 comma 3. It is a reflexive because 1 comma 1 is there, 2 comma 2 is there, 3 comma 3 is there. That's what it is an reflexive. But it is not a symmetric because 1 comma 3 is there, 3 comma 1 is not there. Okay, na? All the reflexive relations are may not be a symmetric relation. Okay, now one more important here, how many symmetric relation we can make on the set A which contain the n number of element. This is very important. If n of A contain the n number of element, okay na, then number of symmetric is equal to 2 power n into n plus 1 by 2. This is a number of number of symmetric relation on a set A which contain n number of elements. Okay, next we will move on to the next relation, that is an transitive relation. Let A be the any set. A relation R on a set A is said to be transitive relation if ordered pair A comma B belongs to R and B comma C belongs to R. It implies A comma C also belongs to R. It should be satisfied for all the element of A comma B comma C must be in the set A only. Okay, look at here, ordered pair A comma B belongs to R and B comma C belongs to R. Then A comma C must be belongs to R, then only the relation is transitive relation. Okay, now I will take as one example here. On the set natural number, the relation R defined by x related to y in such a way that x is less than y is transitive because I will take a 3 element in the natural number x comma y comma z in the natural number in such a way that I will take as x is less than y is less than z. It implies x is less than z. For example, 1 is less than 3, 3 is less than 5, then 1 must be a less than 5. Okay, I will take a one more example here. Let A be the set of all the straight line in a plane. Then the relation parallel to, for example, L1 is parallel to L2. That is a relation, is a parallel to on a set A is transitive relation. all the L1, L2, L3 in the set A, if I will take it as an L1 is parallel to L2 and L2 is parallel to L3, it must and should L1 is parallel to L3. Okay, na? Then we will go to the next one more important example to verify three relations also. Now check relation R for the reflexivity, symmetry and transitivity, where R is defined as L1 related to L2 if and only if L1 is perpendicular to L2 for all L1 comma L2 belongs to set A. What is the set A? Set of lines in a plane. Let me check here. Let A be the set of all the lines in a plane. Given define the relation in such a way that L1 is perpendicular to L2. It is not a, be careful, L1 is perpendicular to L2 for all L1 comma L2 belongs to set A. Let me check with the reflexive. It is not a reflexive because the any line if you take in the plane, it is a parallel to itself, not a perpendicular. That's what the relation R is not a reflexive. Look at any line if we take in the plane, it is a parallel to itself, but it is not a perpendicular. That's what it is not a reflexive relation. Now check with the symmetry. I will take a two element line L1 and L2 in the set A such that L1 perpendicular to L2. L1 is perpendicular to L2 means it implies L2 also perpendicular to L1. Therefore R is symmetric relation. Any line perpendicular to another line means that another line also perpendicular to the given line. Therefore L2 is also perpendicular to L1. Therefore R is symmetric. Let me check with the transitive. I will take a two ordered pair. L1 is perpendicular to L2. L2 also perpendicular to L3. For example, L1 is perpendicular to L2. L2 is perpendicular to L1. Then L1 is not perpendicular to L3 because it may be parallel. It is not a perpendicular. Therefore, we can say that R is not transitive on the relation perpendicular. Okay. Now let me move on to the sorry. One I forget to tell you that for the previous how many transitive relation we can make. There is no such a pattern for the transitive. That's what I didn't define that one. Okay. Now let me move on to the next one, that is an equivalence relation. What is the equivalence relation? A relation R on a set A is said to be equivalence relation on A if and only if that relation satisfies the this three relation: reflexive, symmetric, transitive. Then that relation is called equivalence relation. Okay, a relation which satisfies these three: reflexive, symmetric, transitive, then we can say that it is an equivalence relation. Now I will take as a one example here. It is a relation is congruent. The set A is the set A which contain the set of triangles. The relation defined is congruent. Check with the reflexive. Any triangle is an congruent to itself. Same triangle if you drawing there means it is a congruent to each other because angles also equal, sides also equal because same triangle we are writing. Therefore we can say that ordered pair. Take as triangle 1 comma triangle 1 is belongs to R. Therefore it is an reflexive on set S. which contain the set of all triangles. Let's move on to the symmetric. If triangle 1 is related to triangle 2, it means that triangle 1 is congruent to triangle 2. It implies triangle 2 also congruent to triangle 1. It means that ordered pair triangle 2 comma triangle 1 is in the where it's in the relation. Therefore, the congruent is symmetric on the set S. Okay. Now let me check with the transitive. Triangle 1 is congruent to triangle 2. Triangle 2 is congruent to triangle 3. Must and should. It implies triangle 1 is congruent to triangle 3. Therefore, what we can say that the congruent is transitive on set S, which contain the set of all the triangles. Therefore, congruent is equivalence relation on set S because which satisfies all the three relations. Okay, then how many equivalence relations we can make which contain the n number of elements? We can't see particular formula for that one, but we can say the one pattern for that one. What is that one? If set A contain the one element, it has an we can make as an one equivalence relation. If contain the two element, if contain the two element, we can make as an 1 comma 2. It means that which contain we can make as a two equivalence relation. If the set contain the three element, start with the this second, the 2, 1 plus 2, that is a 3. This 2 plus 3, 5. How many we can make equivalence? 5 equivalence which contain the 3 element. Let me go to the 4. This 1 comma, sorry, we have to start with the 5. I told you 5. Then 2 comma 5, that is a 7. 3 comma 7, that is a 10. Then 5 comma 10, then that is a 15. It means that how many equivalence relation we can make which contain the 5 elements means 15 equivalence relation we can make. This is about the equivalence relation. In the next video we are going to look at the very important examples on this equivalence relation which will come under the board exam. Thank you so much. Bye. Take care.